So welcome to the Project TCS CS Study Group Season 2, where we finally made it. We finally finished the Season 1. That was an achievement. I saw season 1 wouldn't never finish, like eternally, but it finished, and we're finally going to the Season 2. And we have group member changes, and yeah, we hopefully want to finish this until the May, hopefully. Um, so so here is the tentative schedule. If you want to change this or swap this or postpone this, let me know. But let's not postpone too much like what happened in last season. It's not good. Anyway, I'll just get to the point. So the original paper was named Maintaining Information in Fully Dynamic Trees with Top Trees, but I had a feeling that it was not a great tutorial to the top trees. So I felt it was kind of outdated and it didn't have too much information. Like I didn't understand what was top trees. I know I didn't understood what was top trees. So I don't think that was a great introduction. I don't think that's great. So I found some other references, which is mostly by Renato Werneck, and yeah, he provided some interesting new takes on top trees. So the our lecture will be mostly based on the self-adjusting top trees paper by Renato Werneck. So first, I'll discuss the internal structure of top trees and how to implement this. But I won't get too much to the implementation. I'll skip a lot of details mostly because I don't know them. Second, I'll discuss the application of top trees. So if we have that black box, what you're gonna do with that kind of stuff, you know. Uh, so let me recall the three well-known 3DS technique in competitive programming. So we don't really discuss competitive programming a lot in this study group, but I think this lecture is kind of closely related to competitive programming, which is funny because we don't get to such kind of lectures a lot. So I think you guys are aware of three techniques. The first one is well known. It is heavy-light decomposition. I won't explain this. The second one is also well known. It is Euler tree, and the third one is not really well known, but it's kind of something like this. So like usually the context of HLD is to like the point of HLD is to maintain path queries. Like you're given a path in the tree and you want to decompose it into like a log n chains. So that's the usual context of using HLD. But it turns out you can modify the HLD to support some kind of subtree queries and just aggregate the information for the whole tree. So if you have some modification in the static tree, then you can use the heavy light decomposition to propagate that modification toward the top. So for each vertex, it maintains the data structure to aggregate the information from light edges. So like basically you're doing a dynamic programming, but the vertex is not an actual vertex, and the vertex is a path. Like you do a dynamic programming where like each state is basically a path, and there is a substate of which vertex where the element is. So yeah, so to gather this information, we just maintain a data structure for each vertex and for each path. Yeah, I think I'm not sure I'm explaining this very well. I think if you know what I mean, then you probably get what I'm saying. Anyway, I think in Korea we call this dynamic 3DP, but I don't think this is a universally accepted word. But let me just call it dynamic 3DP because just I like that word. Uh, so we know the dynamization of two previous versions. The linked tree is a dynamic version of HLD, and it's known that it's good at edge insertion, deletion, and pass queries. And the Euler tree is a dynamic version of Euler, so it also supports edge insertion, deletion, and subtree queries. So the top tree is not started from the historical context. I don't think top tree was started as a generalization of the modification of HLD, but more like a more, it was from the more complicated concept of topology tree. The thing about topology tree stems back to the 1980s, so it's an old data structure. It may be predates linker tree. So and yeah, the context there was quite different, but Wernick provided a simplified description of top trees, which we will get to, the rate compressed one, we'll get to that. And he provided a connection between the linker trees and top trees. So this is somewhat compatible with what we know as dynamic 3DP, but as far as I know, we can simplify this further. So top tree supports edge insertion, deletion, pass, and subtree queries. Let's go. So in this problem, we assume that the edges are ordered cyclically. What does it mean? So like say we have, so like it's kind of like for each tree, for each vertex, there is a child node, and usually we don't care about their orders, but when we store them in an adjacency list, in practice we have an order for the child. We have first child, second child, and so on and so on. In practically, we have an order for the child, just like we have a planar representation of the tree. Yeah, that 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 doesn't really follows with what actually we define the tree, but practically we usually have it. So in this problem, we preserve that order. We always preserve that order, just because we have to do that. Like this is not a service. We just have to do that. It'll be, yeah, yeah. It should be clear in the future context. So we can consider the two operation that reduces the vertex of tree. The first one is compress. It smooths out the degree to vertex of V. The second one is rake. It takes a leaf vertex and merge it to a cyclically adjacent vertex per the edge ordering. So yeah, for if you want to rake some leaf, you can only put it in like at most two other ones. You don't have, you cannot put it anywhere. You can just put it left or put it right. You don't have a lot of choices for this. And yeah, you can always do that when you have more than three vertices. You can always do this because there is a leaf. It's obvious. So you can always do this to reduce the tree into a single edges. So, so top tree is a rooted binary forest of clusters where each cluster is either a compression of two child cluster, or a rake of one child cluster to another, or a base cluster, which is just a leaf. So the cluster is something what we call as a as a list, as a set of edges, and 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 the cut and the clusters in the actual tree, they form a connected subtrees. So anyway, in the end, the root clusters corresponds to some paths of the tree. Like the root cluster contains all edges of the tree, but it looks like some paths of the tree because like we take two edges and we make it, and we merge it and we make another edges. So the construction is we take two edges and we make new edges from there. So in the end, we have one edges. And if you see that edges, it's kind of like it corresponds to the path. So the root cluster corresponds to some paths in the tree, but the root cluster contains all edges of the tree. So like there is a difference between what I mean corresponds and what I mean contains. So yeah. So the API is the following. So you have a link and you can cut and you can expose the path to be clear. So like by exposing a path, it means you're setting the path, you're setting the root of the tree as an edge of the endpoint v to the w. Yeah. Yes, it's an edge. It's an edge. Yeah, it's an edge. It's an edge which corresponds to some path and which contains all the edges of the tree. So basically our application is like we take this as a binary search tree of the tree. Like yeah, this like if you take the line, then you kind of think like, oh, this is just a split tree. Yeah, you'll get to that conclusion. Uh, so we want to use the top tree as the binary search tree of the tree. Then we need a small depth, and it is possible to construct a top tree with depth 4 log n. I won't get to it, but it's possible, and I don't think it's so hard. But anyway, we are not using that, and we are using the self-balancing strategy. So basically, we are doing something like split trees. So we won't care if the initial depth of the tree is large. So we can just make any kind of tree, and we'll just believe in play. We'll just play where we need and just believe it's fast. So like this is intuitive because when you make a linker tree, you don't really compute the HLD. You don't have to compute the HLD. You just call the access function and just hope it works fine. Hope it just like converges to HLD in per your application. You don't really compute the HLD. You just hope it converges to HLD. So it's just same. For top tree, this is just same. So this data structure does not guarantee worst case complexity, but only amortized. But actually, it's possible to implement this in worst case time complexity, and I didn't know that, but for linker tree, you can also do it worst case. But we won't discuss this. I don't think we have to know this. It's just fine that we just theoretically know that it is possible and somebody was able to do that. I don't think we have to get into that detail. And also we'll just keep for the most proof, and we'll just claim that you believe in play. And we don't, and I think you can just believe this. Like I think you can just believe this is fast and it's usually just like log amortized. So let's initialize the top tree. Of course, we can just add n-1 edges, but this is just an exercise. I just want to show you what kind of invariant you want to have. So you take a leaf node, Z, and make it rooted from Z. So Z is a root. From the future context, we always say Z is a root. And you take any path decomposition of the tree. Every path starts from the leaf and ends at another path or the root. So path decomposition is a partition of edges. So like, yeah, you take the Z and every path just collides at other paths. Every path just starts from the root and collides at other paths or just gets straight to the root. And of course, there is only one path that goes straight to the root. By the way, if you have a question, you can just interrupt. Yeah, I want something like any questions or stuff. You can just interrupt if you have questions. So let's recurse from the root path. So like then if you recurse from the root path, there is a list of paths that ends at the vertices of root paths are. I mean the ones that are colliding to the current path, and like they induces a subtree. So like you take this picture, like you have this path. This is the root path. This is the one goes from A to Z. It's a root path, and there is some path that collides to this. So the path from R collides, Q collides, F, J, X, O, Y, K, T. They all collide to the one. And here we classify this by the edge that was from that incurred the collision. So like here you see the HCD was the end of that pass. So the pass where the pass R collided at the HCD. The pass Q collided at HEC, CE. The pass K collided at HCN. So you can just say something like this. So pass Y collided at pass the HWY. So per the collided edges, you recursively merge it to the clusters. So for example, you just recurse from CE and you take this as a root path. So the path from Q to the C is a root path. And the subtrees that is induced by this, by induced, I mean like here the path Q to the C and the path S to the E is the two paths that will be go to the single cluster. So we recursively think that we recursively consider this as a root path and merge it into a single cluster. So in this sense, each edge incident to a root path forms a single subtree, and we just recursively merge it into clusters. Then we have some clusters hanging in the path P. So that's the picture we'll have. And we care the orders of them. So like here is the end result. This is the end result. This is not the beginning. In the beginning, for each edge, for each vertices VWXY, there could be more than two clusters hanging around there. And what you do is from the right part, you rate them. From the left part, you just rate them. And you just rate inside. You don't go to the path P. You just rate them inside. So in the end, you have these two subtrees hanging there. If you don't have a rate cluster, then now it's just a good time for doing a compression, because if you don't have a rate cluster, it's the path, so you can just merge two adjacent one and half it, and merge two adjacent one, half it, repeat and repeat. So that kind of constructs a binary tree of compression. But we will do similarly here, but note that we have to rake. So intuitively we can rake everything at the beginning, but here we will rake right before the compression. Rake is performed only if it blocks the compression. So there is a lot of details, like the edges hanging in the like edges should start from the leaf or stuff. There are a lot of details. And they are and why those details exist? They are just for some a lot of invariance that this data structure should satisfy. Uh, but but the but the big picture is that I don't think you have to know all the invariants, because maybe you can just come up with better invariants, honestly. So this is one kind of implementation, but I think in general it's just easy to interpret this as a dynamic 3DP. So like each heavy path is, so like you can think that the past decomposition is just an HLD, and you and for each subtree and for each path there is a light edge coming through there, and what you do is raking them. You rake them to form a single data structure, to say, and then you compress it to form a binary tree for each path. Yeah. this is not the only one, and probably this is not the simplest one to implement top trees. Also there are a lot of technical issues, like you have to store the vertex information, but we are not going through there. Let me take a break for like 5 minutes. I think. I think this lecture won't be that long. Yeah, yeah, this lecture won't be that long. I think we can finish in 1 hour. Let's have a break. We'll talk about updates, but here is mostly technical, so I'll skip fastly, and I didn't even wrote a lot of stuff on here. So yeah, we'll define the handle of the vertex V. If the degree of V is at least 2, then NV is the node representing compressed V. Otherwise, it's the topmost rake node that have V as an endpoint. So to provide a small context, so like in the end, you have a tree that is like rake trees, and under the rake tree there is a compressed tree, compress, and under the compressed tree there is a rake trees. So you have an alternating list of trees. That's what you gotta have here, and that is a kind of an invariant. So yeah. So we have this kind of alternating rate compressed trees, and this and and the reason why we raked at the end from the previous one, we didn't compress right away, and we didn't rake right away and compress. We rather just wait until we really have to rake it and then rake and then compress. So the reason why we did that is to make a beautiful tree, like to make a tree where this invariant is nicely preserved. So that's kind of intuition. So so by meaning the topmost non-rake node, so it is like when you have a leaf here, so yeah, I think it's just that node, or no, I think I'm a bit messed up, but I don't think this is important. So anyway, yeah. So yeah, I think it is the leaf of the rake. I don't think it is the leaf of that rake tree, but when I wrote it, then I had other ideas. I'm not sure. I'm a bit confused, but anyway, this point is not too much important. So yeah, just you can read it when you're confused. Yeah. Anyway, yeah, this is how you identify nodes, vertex node for the top trees. So yeah, this kind of you kind of use handles for it. Let's just keep it. So we introduced the basic tool that is play and splice. So splay is the process of escalating a node as a root without changing the represented tree. So I mean the past decomposition is preserved. You don't touch the past decomposition and any elements in between, but the internal structure is changed. From the internal structure, you just escalate a node to a root. So internally a node is escalated to root, so that is a big change. But externally, the past decomposition and everything is preserved. Like it's not like if you do the placing in link a tree, you just change the tree right over there. So yeah, it's just an internal thing. Splice is similar to the access operation of LCT, but it is like just kind of a half-done access operation. Like you don't do the full operation and you just do it step by step. So yeah, you have a pass like this. Say you have a pass like this and this and this and this and this. So let's say we are splicing here. then the new path you're gonna have is this one. No, yeah. The new path you're gonna have is this one, and you cut this, and this one just becomes this. And if you splice it once again, then you also have this and this. And if you splice it once again, then you have this and this. And finally, if you splice for the last time, you have this. So if you think about the linker tree, if you do the access over here, then you just do this right away in a single like in a one operation. Of course, the implementation is like this, but it just does like this. But the splice operation doesn't do it at once. It just do it step by step. So soft expose is a way to extract the path V to the W. So basically you have something like this. Um, you have NV here, and like there are some childs, and you have NW here. So we talked about the handle NV is roughly like a node that represents a vertex of V. It is not, but it roughly works like that. So NV, there's NW, and this is the path here, and there is something another. And between the V and W, there is a path extracted here. So it doesn't really escalate the path to the root, but it makes the path between V to the W very close to the leaf, to the root. So yeah, you can't kind of encounter the similar situation when you try to implement splay trees. When you do the range operation in splay trees, you also just just splay two sentinels, and you do the lazy operation or whatever, like reverse or kind of thing you want to do over this kind of tree. So yeah, I think if you did the play tree, then you probably did the similar thing of soft expose, and it is similar for top trees. Hard expose is just changing the soft expose to the user API, because our guarantee was to make the path between V to the W as a root of the tree. So to do this, we break the invariant and just give it to the root so user can do something. So yeah, but yeah, this is not hard. We just break some invariants and ask for user to do some mutation and just unroll it. Yeah. So yeah, this is mostly an implementation matter. So link and cut is yeah, link and cut is almost follows when you have a soft expose. So you soft expose the edge to cut, then the base cluster have depth too. So this first picture is the original one. If you soft expose, you have this kind of situation. Then you remove this edge and detach the parent vertex like this. Sorry for my bad drawing. You remove the vertex B, you remove the node B, and you detach the V and W, the handle. You detach the handle. Now they lack the right child, but you can just put it from somewhere and attach it. Like you can just you can just find the predecessor or successor per the cyclic order. I'm not sure how exactly we are gonna do that, but anyway, probably you can do it. So you can just attach it, then the invariant is preserved. So for link, you just kind of do it in opposite order. So the takeaway is it's just you just do the soft expose and blah blah blah, and yeah, you can just link and cut. Yeah. So now let's talk about the problems. So yeah, so now let's talk about what problems we can solve with the top trees. So here is the, I think here is the most important part, and let me just talk about the rake and compress scheme once again. So basically top tree is a tree that is composed with these two operations. First operation is that you're compressing a node, degree 2 node, and you kind of smooth out. And the second operation is that you rake the vertex to another, so it is attached to the path of the another node. So here, what we are gonna do is we are showing a lot of cases where we can do the DP on this structure. So if you can do the DP on this structure, then you can maintain that value over the dynamic tree, and yeah. So if you have a appropriate interface, then if you just set the operator straight and just just if you just tell how to lazy propagate and how to merge to childs, then you can just maintain the value. So this compressing and rating is the basic recursive structure, and here we are gonna know here we are gonna see how we can maintain various interesting values over here. uh, Problem one is to maintain the sum of all edge for each component. But we have tirelessly talked about these things. So like the root cluster represents a path, but it contains all edges. So for each cluster, you just store the sum of the corresponding edge weights in child cluster. Like if you're a leaf, then just take the edge value. If you're not a leaf, then you take the child and sum it. Then you can just maintain the sum of all weight of the edge for each component. So this is a trivial problem, and you don't have to even care whether the cluster is rake or cluster is compressed. Any questions? So the second thing is, if you're given a path, we can compute the maximum weight edge in a path in log n time. So if you expose the path v to the w, then the edges inside of the path are compressed and the edges outside of the path are raked. So that is the interface you're gonna see. So like, yeah, so it's like if you expose the path v to the w, then the inside is all compressed and the outside is all raked, like this. Then you have two merge schemes. When you're merging a compressed cluster, you just take the maximum from the child. And when you do a rake, when you're merging a rake cluster, you just ignore the red one. So in the compressed cluster, you do this. You just take both one. In the rake, you ignore the raked one. Yeah, kind of this. Then if you expose this, then you just clearly have a set of edges that only corresponds to a path. So in the same way, you can maintain an ignored max, which is the maximum weight that's not in a path. So yeah, when you ignore an edge by raking, when you do a rake operation and ignore an edge, you just stored it in somewhere else. You just stored the ignored max thingy, and it is a container that stores the maximum of all ignored edges. So yeah, you if you maintain that value, then you can do the same thing. It's just the same thing. And of course, for both problem, you can use sum instead of max. Then you can compute the length of a path. And yeah, we'll in the coming slides, we will just talk about the length of the path, because we are not interested in maximum here, but we are interested in the length. So you can do the lazy propagation too. Given a path, you can add a constant in a path. So compress. So if you're gonna propagate it, if you have a compressed cluster, you just propagate to the both child. If you're having a rake cluster, just propagate it to the original child. That's it. Then you can do a lazy propagation. You can maintain a diameter too. So you maintain the diameter and path length at the furthest point from each endpoint of the path. So like here, so like the funny thing of this is like uh, each cluster contains a subtree, but it represents a path. So each cluster represents a path, and you store the path length which the cluster represents, and you store the diameter inside the subtree, and from this two endpoint of the path, you maintain the furthest point. Then let's look at two cases. First case is where we are doing a compression. Then what you want to know is the diameter. What you want to know is the diameter, and the diameter is either a maximum over here or the maximum over here, or it is something that passes through the vertex V. So you take this farthest point and you take this farthest point and add it. Then you can maintain a diameter because you have all three cases, all here, or it passes between there. The rating is same. It's same for the rating. Furthest point from each endpoint of the path is, yeah, you can just, you have the path length over here. So you can take this one and yeah, this one will go to the W. So yeah, like this. And like this. It is a horrible drawing. I'm sorry, but anyway. Yeah, so you can maintain the furthest point from each endpoint of the path, and rake also same. Path length. Path length is a little bit different, but we how we do it. In compress, we just sum it. In rake, we just ignore the raked one. So it is different for each cluster, but anyway, it's trivial. And why is trivial? Because we have talked about it in the previous problems. Yeah, and we process the query problem. We mark a mark and find the nearest mark vertex in log n time. So let's just assume that there is an auxiliary edges for each vertex. So like we just not flatten. We flatten the vertex into an edge. So we have 2n minus 1 edges and 2n vertices. For each edge, we maintain the closest marked edge for each endpoint and the path length. So yeah, again, we have something like this. Path length and the closest one here and the closest one here. Then yeah, you can just, then you can of course maintain the path length. And if you want to maintain the closest one, yeah, you're gonna want to take this one and this one, or you didn't find anything marked at this one, so you want to go this further and find something else from this one, or Yeah, ditto for this one. No. And ditto for this one. Yeah. So yeah, this 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 information just well propagates in the case of cluster merge. And yeah, for query, you can just simply expose the auxiliary edges for each vertex. So if you mark, you just set the distance 0. If you unmark, you just set the distance infinity. That's it. And you just, yeah, that's it. Yeah. So until this point, we have only discussed with local property. A property is local if it can be aggregated from subtree. So like range sum is a local property. When we talk about just binary trees over lines, then a range query like minimum, maximum, sum, multiple, blah, 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 they are all local. But finding a case elements over an array is not a local property because the child's case element have nothing to do with its parent's case element. It does not propagate well. So in a binary search tree context, if we want to find the case element, we start from the root and descend down the tree. Like 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 I think everyone here knows how to find case element in a segment tree. We just start from the root, and if the left subtree have more than k value, then we just descend to the left. Otherwise, we descend to the right. Yeah, so we want to do similar things on top trees, and we can solve many interesting problems with this. Like, say if you you know, when you think about top trees, then the thing that corresponds to the median of the array, like the medium element of the array, is just a centroid. There is it's a little bit funny, but when you think about it, then it kind of results like that. The centroid is the median. It corresponds to the median of the array. So let's take a look at the following lemmas. So yeah, so basically it means uh, when you have a root cluster, uh, when you have a root cluster, which is just root cluster, which is just this and this, and they have a intersection here at C, and this is the whole tree. This is not a part of the tree. Their union compose the whole tree. So when you take the maximum distance over here, and when you take the maximum distance over here, then if this one wins, then the center is over here. If this one is farther, then the center is here. So you can kind of bisect with this at the top of the top cluster. At the top cluster, you can bisect with this algorithm. And for the center, the same. You don't take the maximum distance, but you just take the size of the tree. For the level ancestor and LCA, we don't have this kind of interface, but actually they are pretty easy because you just expose the path and find the case element like you just do it in the binary tree. Here, the only different thing is you are descending down the compressed tree instead of binary tree. So the binary tree is the sequence of compression here. That is the difference. So if you find the case element in the segment tree, you just descend down. Here you do the same thing, but it's not segment tree, but it's a tree consisted with the compression cluster. So you descend down there and find the level ancestor. And if you know the level, and the thing is, if you can find the distance between two vertex, and if you can find the level ancestor, then you can easily find the LCA by some triangle inequality kind of formula. It is trivial. It is trivial anyway, so you can do it. So you just do it, and it's a little bit easier than the other problems. So here we'll just talk about the center and centroid, and they both have this kind of funny lemma that that indicates we can kind of bisect, but not really, because this only works at the top cluster. This doesn't work in general. This only works at the top cluster. That's why this doesn't give you a solution. So here I'll talk about the funny thing that I will not prove. I will not prove. And so so we can so so we can abstract them as the following function. So given the root cluster, we have a choice function that decides where the desired vertex or edges lies in. So the previous two lemmas, they can be expressed as per this choice function context. They fit well in this choice function context. So with the choice function, we want to bisect the candidate set of the answer. In the beginning, the candidate set is the total tree, is the entire tree. And it is trivial to reduce them by half. We just talked about that. But the hard thing is how to descend further. We can do one step, but how to do it further and further. Uh, we can modify the top tree so that the child of C lies in different child for root cluster. So it means like, yes, say, and I'll not show you how, because actually in the actually I think the guy should prove this, but the paper doesn't mention how to prove this. I was a bit irritated, but anyway, uh, you have the root cluster. Here's a son. Here's a son. Blah blah blah. Say that the candidate set is here. Then you have this stuff. Then you want to bisect this one. So this is a candidate set. Say this is a candidate set. Then you want to see whether here is your answer or here's the answer. So what we can do is we can put this over here somehow. We can just put this over here. We can modify the top tree to do that. How? I don't know, but we can do it. So if we do it, then we can just like we just like split the C into half. Then we can just bisect like what we did before, and then the verdicts of choice are again decide whether we take the left son or right son. Any questions? Because this is the end of the lecture, so let's get a question and go to the concluding remarks. So yeah, so yesterday Andrew I talked with him and he just shared us an implementation of the top trees. So the interfaces are identical. The actual implementation, I think it's more simpler. I think yeah, yeah, it's more of a competitive programmer context, so it's much easier to understand. So if you want to implement this, it will probably be a helpful resource. You can just take through the link there. So yeah, and I'm also sorry for not demonstrating how to do subtree queries, but it's in that, but the code there does the subtree queries. You can expose the subtree, like you can expose the subtree nodes toward the top of the tree. I don't exactly know how, but I think intuitively, like, yeah, it seems you can do it. I think, yeah, it makes sense for me. So yeah, if I did the implementation before this lecture, probably I can talk in details, but but it was like, yeah, I didn't had a very pleasant week before here, so yeah, I couldn't do that, and I'm sorry for that. So yeah, maybe I'll maybe I'm trying to implement this in next weeks or so if I have time. Yeah, so that's it. And I'm very glad to finish my lecture in 1 hour. Yeah. Any questions? Okay, then see you.
See, see you.